So today we're going to start a new chapter. We're going to be working on ionic compounds and ionic bonding. And again, I'm going to follow along with your PowerPoint just to kind of help you stay with the notes and stay on track with the rest of the class. One of the things here that we need to work on is remembering valence electrons. So the electrons in the outermost level or shell we learned are called valence. You can figure out how many valence electrons something has, at least for the S and the P block, by looking at the group number. So remember, these guys all have 1 valence. These have 2. These have 3, 4, 5, 6, and 7. And this column has 8 with one exception, helium. Because remember, we talked about helium being actually over here in terms of his electrons, so he has 2. So that's kind of a review from last unit. We also, last unit, talked about how atoms in the same column, my alkali, my alkaline earth, my halogens, etc., they have the same basic properties because they have the same number of valence electrons. We also talked about Lewis dot diagrams in the last chapter. That's another thing that'll come back up again. So for a Lewis dot diagram, you take the element, we'll say calcium, and you place dots for valence electrons. There's 1, there's 2. Okay, if we did something like phosphorus, we go back to our periodic table. We find phosphorus. Phosphorus is right here, so he has 5 valence electrons. So that would be 1, 2, 3, 4, 5. Got to have them single before they double. So that's kind of our review. So everything with this ionic bonding chapter is all about stability. Things want to be stable. Stable means having a full valence electron shell. That means the full outermost shell. If I draw sodium, okay, sodium goes up to 3 levels of electrons. So when we look at sodium right here, sorry about that, when we look at sodium right here, you'll notice that sodium has 1s2, so that's 2 electrons in level 1. Then he has 2s2, 2p6. So that is 8 electrons between the s2 and the p6 that he has in level 2. Then he has 3s1. Okay, so we have 1 electron out here in level 3. That's not stable. To be stable, he needs to have a full outer shell. That means 8 electrons in his outermost shell. So for sodium, that means he's either got to add 7 to this outermost shell or lose that 1 from the outermost shell. It's the only way he can be stable. So that's really what we're going to be talking about today, is how that happens in different atoms. So remember what we had learned before. Atoms are neutral. Okay, so in the atoms, your protons and your electrons were the same. That's how you end up neutral. Your positives and negatives are the same. But today, we're going to be getting into ions. And ions are elements with a charge, where your protons are no longer equal to your electrons. So remember all those charts you did from Unit 3, atomic number, mass number, protons, neutrons, electrons, where your protons and electrons were always the same. But I told you it wouldn't be like that forever. It's not like that anymore. Now, when we're going to be looking at ions, you have to remember protons and electrons are different. But you cannot change the number of protons because protons are what identifies an element. So the only thing we change are our electrons. So, quick summary before we get into the meat of today. Protons are what distinguishes elements from one another. Okay, so elements differ by the number of protons. Neutrons are what differs when we're talking about isotopes. So isotopes differ by the number of number of neutrons. And then today, you learned both of those before, we're adding the third, which is ions. Ions differ by the number of electrons. All right, so let's get started today. Basically, you can either form an ion by gaining an electron or losing an electron. Okay, it has to be one or the other. So there are some atoms that lose electrons. Okay, to achieve their noble gas configuration. Let's go back to sodium again. Sodium, if you remember, okay, and forgive my quick messy drawings, we had 2 here in level 1, we had 8 here in level 2, and then we had 1 left in level 3. So logically it tells you it's a lot easier to lose 1 than it is to gain 7. That's sort of kind of common sense. So what's going to happen to sodium, believe it or not, is this guy is actually going to go away. Okay, that one is going to go somewhere else, and we'll talk about the somewhere else in another video. So when he gets taken away, here's now my sodium. Okay, all of a sudden I have a stable sodium atom. But it's not neutral anymore. Still sodium, it's not actually a noble gas, it just has the electron configuration of a noble gas. But what happens is sodium now has a positive charge. Now that's something you're going to have to get your brain wrapped around. Losing an electron gives you a positive charge. And the reason for that is electrons are negative. So neutral sodium has 11 protons and 11 electrons. That makes it neutral. But this guy right here still has 11 protons, but now I've only got 10 electrons. So that gives me a positive 1 charge because I have 1 more proton than I do an electron. So it equals positive 1. So in terms of notation, you can say sodium has a positive 1 charge. We write it as a superscript, like an exponent. You can say sodium is a 1 plus. It's also perfectly acceptable. Honestly, if it's a 1, you can actually just say Na plus. All of those are correct. And any time a situation like this where you lose an electron and become positively charged, it is called a cation. Okay, cations are positively charged ions. And this is what happens in all of our metals, all of them. So, joys of the periodic table, of course there's going to be a trend. The trend with the periodic table is everything that's a metal. Okay, so let's draw my little staircase in here. Everything on this side of the staircase is going to be a positive ion. So we just said sodium becomes a plus 1 because it loses 1 electron. Well, think about it for a second. Okay, these guys right here all have 1 valence electron. So believe it or not, everything in this column is going to become a plus 1 ion. Oops. My next column all forms they all have 2 valence electrons. So because they have 2 valence electrons, these guys, when they lose those 2, are going to be a plus 2 ion. These guys down here, because you know we're skipping the D block because it never makes any sense, these guys have 3 valence electrons. So again, if we think about choices, I can lose 3, I can gain 5. It's easier to lose 3. These guys become plus 3 ions. Okay, so instead of having to draw the diagram every time and look at what happens, one of the things you can do is simply learn the periodic pattern. Plus 1, plus 2, plus 3. And we'll get to the other side later. The other way we can do this is we can look at dot diagrams. So the one in your notes has calcium. Okay, put my 2 little dots on here. So calcium can either gain 6 and be full or lose these 2 and be naked. Now in reality he's not naked because there's another level beneath it. But it's easier to visualize that with dot diagrams. So we know losing 2 is going to be the simplest way. So what we see is that these 2 electrons come off. This is how we do this with a dot diagram. And what we're left with is calcium. And because he's lost 2 electrons, he has a plus 2 charge. Piece of cake. Second thing that can happen is atoms can gain electrons. If you gain electrons, I want you to think about this. Let me draw you chlorine. Okay, chlorine has 2 electrons in that first level. Okay, the second level has got that S2P6, so that's going to be 8 of these guys. And then in my third level, when I look at chlorine, it actually has 7 valence electrons. Okay, so 1, 2, 3, 4, 5, 6, 7. So he's not stable. Okay, he's definitely not stable. He's not full. So the choice is, do I add 1 or do I lose 7? Again, common sense kicks in. It's going to make a lot more sense to have 1 added. And we'll talk about later where that comes from. That makes chlorine a negatively charged ion. And a negatively charged ion is called an anion. Now, again, it's becoming negatively charged by gaining an electron. That'll mess with your brain a little. But think about it. Neutral chlorine, 17 positives, 17 negatives. That makes it have an overall charge of 0. But my drawing over here, I still have 17 protons because it's still chlorine. Now I have 18 electrons. That gives me the -1 charge. Just like before, you can do notation different ways. Cl-1 is fine. Cl1- is fine. And Cl-. Okay, all of those are accepted. Your SOL usually prefers you include numbers. In fact, they make it pretty picky. This is, by the way, what happens in my nonmetals. So everything on the right side of the periodic table staircase is going to gain electrons to become that noble gas electron configuration. So let's look at the periodic table again. If I look at the other side of my staircase, let me draw my little staircase back in here. And I know I always do different things at the bottom down here. Just remember, it's because we're not 100% sure what these guys do. Okay, we just don't know yet. Everything on this side, my nonmetals, are going to form these negative ions. So again, we can see the pattern. We said that these guys were +1s, these were +2s, these were +3s. Well, noble gases aren't going to do anything. They're already stable, so we kind of skip them. But starting with fluorine, chlorine, bromine, iodine, astatine, these guys have 7 valence, so they need to gain 1 electron, giving them a -1 charge. Oxygen, sulfur, selenium, they got to gain 2, gives them a -2 charge. Nitrogen, phosphorus, arsenic, gives me a -3. Now notice I stopped at arsenic, okay? Believe it or not, once you cross this staircase, then we usually don't see this happening. We are really sticking to these non-metals. Okay, so as we look at this pattern, you'll notice there's one column that we didn't give a number to. This one right here. Think about it. Carbon, silicon. If they kind of want to become an ion and be a noble gas, it's going to be +4 or -4. Well, neither one of those is real easy to do. So the reality is they don't. We'll get into carbon in a later chapter. Carbon actually does other things. There's other kind of bonding. The one exception in this column, or I should say the 2 exceptions, are these guys right here, tin and lead. Tin and lead will act like transition metals. So we'll come back to tin and lead later, but they really do act like these transition metals even though they're in this column. Okay, so +1, +2, +3, -3, -2, -1. Vital for you to know that. All right, but if you do forget it, you can once again do the dot diagrams. So let's go back to phosphorus. Phosphorus has 5 valence electrons. So again, I'm going to either strip 5, make him naked, add 3, make him full. Seems a lot easier to me to add 3. So I can use my arrows, show how I'm adding these 3 electrons, and then since I've added 3, that gives me a -3 charge. Yes, it takes some time to get that straight in your brain, but it really is key that you know adding electrons gives you a negative charge. So you've got quite a few practice problems in your notes. Definitely recommend that you try those. You can actually always double check your answers online. You can double check your answers with me. But for this video's sake, I'm going to move on to transition metals. Transition metals are weird. They're always weird. The only thing I can tell you for sure is they form cations. They form positives. But it's really hard to predict what they're going to do. I can't show you a pattern on the periodic table that says this does this, this does this. There just isn't one. In fact, sometimes they form more than one ion. Iron, for example, can be a +2 or a +3. And there's no way that you in this class are going to know what it does. So the beautiful thing is you will always be told. You just need to remember that they are always positive. Okay, so the last little nugget for today, or I'm sorry, one of the last 2 nuggets, is how do we name these ions? This is so easy. Naming follows IUPAC rules. That's the International Union of Physical and Applied Chemistry. They're basically people that make the rules. And it's really simple. For cations, you simply add ion to the name. So while Ca is calcium, okay, that's easy enough. If we have Ca +2, we name it a calcium ion. Yes, I'm being serious. That is all you have to do. Okay, it really is that straightforward. And believe it or not, you have to have that word or it's wrong, and that's the #1 mistake people like to make on quizzes. For anions, we change the ending to IDE. So you sort of already knew this, okay, because you guys have seen Cl before, okay? Sodium chlorine is not what you call salt, okay? You call salt sodium chloride. That's where that name comes from. So a lot of the negatives are really simple. Fluorine becomes fluoride. Bromine becomes bromide. But some of the rest of them get a little more complicated. So just kind of stick with the rule that it's usually the first syllable that gets IDE added to it. Now, that's not always the case, but usually. Nitrogen, unfortunately, does not become nitrogide. I personally think that would be absolutely awesome. It becomes nitride. Okay, oxygen does not become oxygide. Again, that would be cool. It becomes oxide. The other naming thing you have to keep in mind is the transition metals. The problem with the transition metals is there's different charges. So I can't just say this is an iron ion and this is an iron ion. Okay, I've got to know the difference between them. So all we do for transition metals is we use Roman numerals to give us the charge. We still say it's an iron ion, but we write the Roman numeral that is equal to the charge. So this is an iron 2 ion. This is an iron 3 ion. For the record, if you put tops and bottoms on them or don't put tops and bottoms on them, it doesn't matter. But you do need to learn your Roman numerals 1 through 10. So if you don't know them, you need to go look them up. You need to know that. The last thing you need to know for the day is polyatomic ions. Polyatomic ions are kind of nifty. Poly means many. So everything we talked about before was like one element by itself or one atom by itself that lost electrons. Polyatomic is a whole group that's stuck together, and as a unit they've lost electrons. And we're going to work with them a lot in the next chapter. So there are 6 of them that you are responsible for memorizing. You need to know their names, you need to know their formulas, you need to know their charges. Okay, period. There's no way around it. You have to know them. So, for example, phosphate is PO4. That's the formula, and it has a -3 charge. Okay, carbonate, and these are all on your PowerPoint, is CO3, and it has a -2 charge. Sulfate is SO4 with a -2 charge. Nitrate is NO3 with a -1 charge. Hydroxide is OH minus. Okay, it means it's OH with a -1 charge. And ammonium, that's not the same stuff you buy in a bottle at the grocery store, is NH4 with a +1 charge. Okay, there are a couple tricks to remembering this, but start off just by trying to memorize them. There's only 6. It is totally doable. See you next video.